Cool. All right. Okay, that was a lot. For the people on Zoom, can you type in the chat? Let me know you can see the screen all well. Very nice. Okay, cool. Okay, hey everybody. Wow, there's so many people here today. Wow, and y'all like sit like way in the back too. Okay, I see how it is. No, it's okay. I hope everybody's doing well. We're almost done with the semester. Yay! It's Wednesday. That means homework 7 is going to be due next Monday. Notice the new date change, so not on Wednesday anymore, but on the Monday. We released it on Monday or Monday evening. So after homework 7, the homeworks are like a lot easier to do. Meaning, homework 7 is your last coding homework. You know, like pat yourselves on the back. You're like almost done. Like you're almost done learning all the code that we're going to teach you. Like all the basics of Python are in your head now. We're not really going to teach any more like basic Python principles like object-oriented programming or like lists or arrays, anything. You're done with all that. You can officially say you know Python as soon as you finish homework 7. The rest of the course is really geared towards like professional development and kind of like inspiring lectures in the sense that like we'll teach you a little bit about how research works. We'll teach you a little bit about how to be like, you know, like carry yourself as a professional in the field, how to stand out, how to write like a good curriculum vitae, how to make a website, stuff like that. And we'll kind of sprinkle in some really interesting things like machine learning maybe. Today I'm going to talk to you about my favorite thing, simulations, and hopefully get you a little inspired in that way. But everything else for the rest of the semester is supposed to be super chill so that you can start emphasizing a lot more time on your projects. So hopefully that will be a bit of a nice thing to hear. For example, homework 8 is just going to be to write your CV or your resume in LaTeX. That's it. So it's not nothing too crazy, no crazy homeworks anymore. Hopefully that's good. And homework 8 will be due not next Monday, but the one after. So everything will be due on Mondays now. Make sure you start on your final projects. We will, like after lecture today, the staff will meet and we will start sending out feedback to you. So you should get feedback in the next couple hours or so. But everybody's projects are roughly good, just a little critiquing on like how it could be a little bit better or maybe simplified down a little bit so it's not too out there, but everything is roughly a good ballpark. So you could definitely start working on your projects for sure. So we encourage you to have some good stuff ready by next week because next Wednesday, we're gonna do check-ins. So we're gonna literally ask you like, what have you done so far? It's not like meant to like scare you into like having results or anything, but we wanna make sure that you haven't not started. And we can tell when you haven't started. So please like put some effort into like thinking about how you're gonna start writing code. Try to write some code. It doesn't have to be like a full working model or anything like that. It doesn't have to be any like line limits or anything like that, but we just want you to, we want to see that you're trying at least to start. And that way you can ask questions and hopefully have some questions for us when we do check-ins next Wednesday. So is there any questions about that? Okay, that's my announcements for today. So let's move on to the material. We're talking about simulations. So this is like my thing. I love this very, very much. It's what I do research in, or what I want to do research in, and I've done it, dabbled it here and there. But it's like what I think the coolest thing about physics or astrophysics is. So we're gonna dive into that today, and you'll learn how to write simulations, which could be useful for your project if you're gonna do that on a rough level. So for example, I felt like it would be some cool stuff. This lecture is not really meant to be like super rigorous or anything, or like you're not gonna get tested on it in any way, shape, or form. But I thought it would be really cool to just show you some cool shit. So for example, this was a final project from a few students the first semester we taught it, this course. And this is like a simulation of the TRAPPIST-1 system, which is just like another solar system like our own. And they have like some cool sound effects. I don't know if people on Zoom can hear it, but it's 2001 Space Odyssey playing. I had it like evolving over time. So you can see how many days and stuff like that. It's pretty cool. Okay, we're not going to play that for 2 minutes, but regardless, you get the point. You can evolve it over time. This is like 1 billion meters by 1 billion meters, and like they're like or simulating all the planet orbits and stuff. It's pretty cool stuff you can do. So that's just like a small example of what you could do, like for your project if you were simulating like a solar system. But it could be a wide range of things. We had people simulating pendulum, like with magnetic fields in them, Rutherford scattering, you name it. Just a whole bunch of just like different, anything that could use the laws of physics can be simulated in some way, shape, or form. So the world is your oyster in terms of what you want to do. Now, if you want to do like partial differential equation stuff, kind of tough. Take another class first before you try. It's going to be really hard, but for a lot of systems with basic ordinary differential equations, you can do a lot. So I just wanted to give you an example of a really cool simulation. Now, the key concepts for a simulation, or the key principles that you have to keep in mind, are the following. So each time step you take in your like physical simulation, you need to increment all the relevant values that change with time. So that might be your positions, that might be velocities, acceleration. Maybe it doesn't necessarily have to be like those like fundamental like particle things that you might think of. It could be something like phase. It could be like the brightness of a star. It could be like the mass if it's changing or something. If you have like winds leaving a star or whatever it may be, some quantities are going to be changing with time, and those need to be updated every single time step. So you need to have a way of solving for these values with like, you need to have the computer know or like have some equation that governs how it gains or loses those quantities with time, how those quantities change. So that's where your differential equations come in. That's where F equals ma. That's where, I don't know, whatever it is, whatever equation, like the spring equation, wherever those might be, that's where they start coming into play, is like in telling your simulation how to update those values. And then you have to continue incrementing time steps until a sufficient time is passed. That might be 100 time steps. It might be 1,000, might be 10 billion. Those time steps can mean different physical times. You set that in your code, like just by what units you plug in with, or like however you scale those quantities. So for example, you can have like a set limit of 5 million years in code time, which is like maybe 100 time steps where you're taking like, little incremental like portions of a million years every time step. Or it could be like on the order of seconds or milliseconds or whatever it is you want. You can have like some physical time scale for your problem, and you can like break your time steps up according to that. So that sounds a lot like a while loop, where we keep iterating until we hit a sufficient condition or like a time limit we want. Not a for loop where you have like a list of things you want to iterate over, but a while loop where you keep going until a condition is met. So maybe you pass the time limit, maybe you're keeping track of like the mass and it loses enough mass, whatever it may be. You set some condition to stop your simulation after however many time steps you take. Are there any questions about those key principles? Just to reiterate, you need to increment all the different values that depend with time every single time step until you hit a time limit or like a condition that changes or that causes you to stop. Okay. We'll keep going. So that loop, that while loop that I just said, is called the main loop in a simulation. So the main loop is like everything runs inside of this main loop. This main loop is responsible for running the whole thing. When the loop stops, the game, or I mean, the simulation stops. So if you stop the while loop, this whole simulation stops running. And inside of that while loop is where we handle all of the different things we need to take care of. So the 5 key points that need to happen inside of a main loop for a simulation is get the relevant values you want. That's like position, velocities, acceleration, time, etc. Then you calculate the changes from physics, like I said, and then you apply those changes to the old values. So like v plus dv, x plus dx, t plus dt, where you can use a derivative, dx dt, you multiply it by some dt, and you get like a dx. This is like Euler's method, if we remember how Euler's method worked. That's one example. There's different, more complicated ways to do it, but the most basic idea is like Euler's method, where you can like incrementally change those like those positions and velocities and times with every single time step. And then you just need to draw your results to a screen, hopefully so people can see it. And then you just repeat. So you draw, and then you update the values, and then you draw again, and you update the values, and you draw again, and so on until the end of the while loop. So that's like the 5 points that need to happen inside that main loop. Okay. So I think now is a good time to transition into writing a game. So this is kind of like what makes this like fun. we're gonna like write a video game in class and we'll play it and I'll show you exactly how it works. Pretty cool. And I think you'll understand just about everything inside of it. There might be some syntax from like a library or whatever, but the main ideas will be pretty clear, hopefully. So let's write a game. Step one, you need to make your object. So you need to initialize, you need to like tell the computer what's gonna be in my game. Now this is a really abstract concept, but like we learned object-oriented programming last time. So oftentimes you wanted to calculate physics, a really useful object to have would be a vector. That would allow us to keep track of like 2 or 3 dimensional positions, velocities, accelerations, forces even. Those are all vectors. So literally just copy over the whole vector class that we talked about last time. Claire talked about it, where you make the class object of a vector, or the constructor. It has like some X and Y, and then you have a whole bunch of methods that allow you to calculate things like the length of the vector, how to add the vectors to each other, how to subtract them, etc., dot products, things like that. You'll get a lot more practice with this on your homework. Homework 7 has a problem where you use this, and I think it'll be really helpful for you to see how that works. So that might be something like an object that we want in our game, but that's a little bit abstract. Maybe a more non-abstract one is, let's say we're playing Pong. What are the objects in Pong, right? That's like the 2 like paddles that go up and down and you have a ball bouncing around. Can somebody tell me what the objects are in that system, in that game? Anybody? It's like the ball is one, and then what's the other type of object we have? The paddle, right? And we have 2 paddles, so we need to make a class called a paddle that like allows us to create multiple paddle objects. And we do that. There's a paddle class here, for example, and like a ball class. So that paddle might have some position and velocity, which we use making vectors. And then we have maybe a width and like a height for a paddle. It's like a rectangle, right? So that sounds pretty reasonable to me. The ball, what are some characteristics of a ball? They have like a radius, maybe a color, position, a velocity. Pretty simple. And then you can create objects from those classes. So we make like a ball from the ball class, a right paddle from the paddle class, a left paddle from the paddle class, where X and Y are like positions. So we're setting one like all the way on one side and the other all the way on the other side. And then we make like a list of paddles from that. So we're just making our objects for the game. We're not doing anything to them yet, but we're just creating them. And it'll make it a lot easier to update these objects in the game. Does that make sense? For like kind of like updating like maybe their positions with time, every time step and stuff like that. Cool. I'm gonna hide these really quick. Hide controls. Cool. So step 2 is like after making those objects, we need to initialize everything. We need to start up the game. We need to like kind of like just make all the starting values. So there are a few different ways of doing this. I found that like making like a main function that hosts our main loop, that while loop inside the main function is kind of like what I call the main loop. In this example, I used a library called Pygame to do a bunch of this stuff. It's just a library though, like it's just a bunch of features of this library that you'll see like how it works in a second. But like a lot of the syntax stuff like pygame.display or like all that stuff, not important. It's not important. All the stuff on the left-hand side down here. But on the right-hand side, this is more what's important. So inside of our main function, we're gonna have initialize some score for like the player in the computer. Start out at 0, it makes sense. And then we start with like some initial speed or like of the ball. It's not important. But what is important is this while loop. So while true, we have like get input, move, collision, score, and draw functions. So one function is going to be getting input from the user, another is going to be moving things, collisions, scoring stuff, and drawing stuff. We'll talk more about those in the next slides. But everything happens inside that loop. That's all I want you to get from this slide. It's just that every little thing that can happen in the game is going to be updated every single step of this while loop. Okay. And on the left-hand side, it's just like a bunch of stuff to like start drawing like a screen, like it'll make a pop-up window. I set some color values like blue, like RGB values for black, white, red, blue. Those are tuples. Not super important how I make all that stuff, but that's like a feature of the library itself. And you'd have to do some Googling on how any specific library works like that. But this library is how you use that. And then like, yeah, so like we make this main function. Is there any questions about this slide? Okay, so we'll move on to the next one. So step 3, this is kind of like an optional step for a video game specifically, where you get input from the user. So the point of a game is so that you can play it, you can interact with it, you can change what's happening in the game to try and win the game, right? So the game needs to have some way of getting your input every single loop step. So this is a bunch of syntax from the library that I'm using, all this like key up, key down stuff. But mainly all this whole function is doing is just checking to see if I press a button on the keypad, what should I do? So like the way I have it set up, I have a bunch of if statements. If I press the up key, move the paddle up. If I press the down key, move the paddle down. If I press the space bar, start moving the ball around when you start the game, stuff like that. All this stuff is just taking a bunch of if statements to check whether or not the user is pressing buttons, and then interpreting those buttons into things that change what's happening in the game, like those positions and velocities and stuff. So this is how you make a game playable. You have to take in those key inputs. But if you don't make it playable, and you just get rid of this whole function, then all you're doing is a simulation where, right, like for simulations, you don't want to be able to change what's happening in like the physics in real time. That's like, no, you want to actually like simulate physics. You want to see what would happen if you let it run loose. So that's like the big difference between video games and simulations. And then step 4 is just adding your physics functions. So for example, if we're making Pong, right, we have these 2 paddles and we have a ball bouncing around. What happens when a ball hits a paddle? Anybody want to give a guess what should happen if I have a ball hit a paddle this way? It should flip directions. Exactly. Does it flip directions? If it's going left, which way does it flip direction to? Does it like go up, down, left, right? It should go right. And similarly, if it's going down, it should keep going down. So if it hits one wall, if it hits a left wall, it goes right. And if it hits a bottom wall, it should go up. If it's a top wall, it should go down. If it's a right wall, it should go left. Right? So it'll kind of look like this. That's just a bunch of if statements, just checking whether or not it passes this boundary. And if it does, flip the velocity by a minus sign. So you see that times equals -1 in all those cases. Just a bunch of if statements checking, where I just flip the velocity. Now you could add something like, I don't know, you can make it speed up every time it hits a wall, make it hyperelastic collisions by making it 1.05 or so whatever, some extra, like greater than 1, it'll start speeding up, where we're just changing the velocities. Or you can make it slow down, aka friction, by like changing it to a 0.95, for example, where it slows it down. But this is just physics, where I'm just checking to see if it collides with something, flip the velocity in the way that it needs to. And then similarly, once we know what needs to happen to our velocities and positions and stuff in our collisions, it's like a collision detection, then we have a move function, which handles the movement of all the things in our game. So for example, all we have to do for like each paddle, the position gets updated by just adding the velocity of the paddle, which changes if you press the buttons. So if I press the up button, I add some velocity to my paddle, which will add some position or change some position. Remember, these are vectors. So if I just add them, it's just adding vectors. And then for the left paddle velocity, that's just like the way I like code it. It's like an AI. It's not really like learning or anything, but I just made it so that its position or its velocity just follows whatever the ball's velocity is by like some like slow factor. So it's not perfect. It's like 95%. So in theory, if it gets really, really fast, you should be able to beat it, but most of the time you're not. So I made it really hard. But anyway, you have some function that handles the movement of all the objects, just updates those physical values based off of the velocities and times and all that stuff. There's more to it. I cut off some of it, but just that's all the function is doing, is just updating those positions and velocities in our game, and then something to handle collisions. Okay, is there any questions about this so far? Okay, we'll move on to the next step. And then step 5 is just have a way of keeping score. So this is a game, right? So you want to win. So you need to have a score for the player, and you need to have a score for the computer. Start by setting them equal to 0. And then basically all we have in the score function is just saying that if the ball goes past the computer's paddle on the left side, add a point to the player. And if it has a like a score, or if it has a position to the right of the right paddle, add a score to the computer. That's all we're doing. Just 2 if statements. And then you just reset the ball to the middle. That way it's like you could start again with some 0 speed. Okay. But for example, this doesn't necessarily have to be like, this is Pong. This is one example. But for example, you could keep track of other things like in a simulation. For example, how many times do asteroids collide in your n-body simulation? That could just be something as simple as if the positions equal each other for like, one of or 2 of your giant, maybe 1,000 or 100,000 particle n-body sim, if they collide, you just add a tally. And then now you're just keeping track of collisions. That's just a useful quantity. There's a lot of different other examples. Maybe how many times does your pendulum reach a certain height? I don't know. You can think of a bunch of different other things, but this is something that you kind of think of as yourself. Like, what information do I want to keep track of in my simulation? This is a score, I guess you could say. In a game, it's an actual score, but in simulations, it's very similar. It's just like when you reach a special condition, keeping track of it. And then I think this is the last step, is drawing the simulation. So like you want to draw everything that's happening, right? There's a whole bunch of stuff going on, but you want to see what happens. Don't worry about any of this. This is all like syntax. Like basically you can do the same thing just by like plotting in matplotlib, but this is just a library. So a lot of this stuff is like only for the library. So don't try to read the code from scratch. Just know that it's drawing, it's updated. It like takes the positions, the widths, the heights, the radii of the ball and the paddles and all that stuff. And it just draws it onto the screen in some colors and stuff the way I want. And it prints some text to keep track of the score. This will be different for Pygame or Matplotlib, maybe even VPython if you're curious about using those libraries. And that's just on a case-by-case basis. But we all know how to plot in Matplotlib. So if I wanted to plot the position of a particle, you could just plot the X and Y coordinate and then just update it every time step. And you have like it'll play like an animation. We did animation. So it's kind of the same idea. In fact, it is the exact same idea. Just this is a different way of doing it with a different library. So we draw at the end of that step. And then the result is something that looks like this. It's like Pong, the GIF. But we can actually play it. Should we play it? We could, it would be, yeah. So all I have to do is just run this file from the command line. I just wrote like all that code into like one like Python file, not like a notebook. But I guess you could do it in a notebook, but I think it would break. You kind of need to have to do it like in a file. But if I run it, it'll make a pop-up window like this. And if I press the space bar, it'll start moving the ball. That was a really bad one. It's really slow. I think it's because oh, that's why. So the speed of everything is slowed because I'm recording the screen for Zoom. So it's not updating as fast. But when you're playing normally without a screen recorder, the ball moves with the speed of however fast the frame rate of your computer is updating. So it's hella slow right now. My bad about that. I just pressed the space bar again, so it changed the direction. But yeah, it's pretty lame this way. I didn't know it would do that, but yeah, and that makes something like this. And I just wanted to show another example, which I think is really fun, that we did in my physics 77 class. We made a pool game. I think we just do main.py. So this is a different game, similar. Oh, it's really loud. Okay, I'll try to keep it quiet. But anyway, you can add audio, you can do a whole bunch of stuff. And now like this is like a pool game. So if I hold back the space bar, for example, it like collides the balls and it does a whole bunch of stuff. All the same, like everything is like basically the same, just like I have a different score counter. If it hits the pockets, it's a different score. Collisions, it's a little bit more complicated because you have balls hitting each other instead of walls. But yeah, we can like, yeah, pretty cool. And then I made some commands. So if you press like W and then Q, you win. If you like sunk all the balls and then it like, okay, that's like obnoxiously loud. But just bear with me. The reason why we did that was because I took the class, like an end game came out like that week of the final project. And it was like, everybody was super hyped for it. It was super cool. The professor clapped, made me feel good. But anyway, So you can add like cheat codes, like if the player presses this, then do this, you press this, then you do that, whatever. But all the same, if we just look at the file, you'll see it's very similar. We have a whole bunch of functions. We have that main, we have the while loop. This was back when I was a novice, so I didn't think to put all the stuff in different functions, so it was really messy, but like it's a lot better to have like self-contained functions. But all the stuff is happening in this while loop. We have some functions like collision detection or like how to move, stuff like that. Kind of cool. Score, it's kind of messy. Initialization at the very top of like a bunch of stuff. We have that same vector class. We make a bunch of objects like from the ball or class and whatever, and stuff like that. So I just wanted to share that with you, that you can do like, this is a very simple, like Pong is a very simple example. It's probably the easiest game you can code up, but the same ideas still apply. You still have like the move function. You have a bunch of like quantities like X or velocity, position, or whatever. You want to update with every time step. You get some input from the user. You change those things based on what the input is and all the physics. And then you just draw it and you repeat over and over and over again. Or if it's simulation, the difference between a video game and a simulation, a video game asks for input for the user to change what's happening, and then simulations don't. Simulations just have a bunch of set of physics rules. Typically, they're a lot more complicated than what you're putting in a video game because you're actually caring about being like physically accurate, whereas a video game just tries to look cool. So nobody cares if the ball like doesn't perfectly like match reality. Nobody cares. It's a video game. It's just supposed to be fun. But for a simulation, we do care. So we have to be really precise with those physics equations. And that typically involves like using those more advanced like differential equation methods that we talked about, those Runge-Kutta methods and like a whole bunch of stuff that we didn't really go into depth with, but like SciPy ODE int way back when we learned about what that is, that's like a more accurate version than like the Euler method, for example. But maybe a video game might use the Euler method because it's a lot easier to code up. It might even be faster, but it's not accurate. But who cares when it's a video game? So yeah, simulations just have a set of rules, physics rules that you have to tell the program how to do each iteration corresponding to. And then simulations are easier to code up than video games. You don't have to worry about input. Think about this. So like imagine I'm coding up, I don't know, the next Call of Duty or something, and I have to include physics for collisions. I have to include physics for like you know, bullets flying around, people jumping off of stuff, planes exploding, whatever, all that violent stuff. But you have to have physics for everything there. Not only that, you have to communicate between, like if a player presses something on their controller, they have to tell the system or whatever to change what's happening for that one player. But then they also have to communicate across the internet with like hundreds of other people at the same time and update at a smooth like 60 frames per second. 60 times that while loop has to iterate every single second with everything happening all at once. That's a big task to accomplish. And it's really difficult. And you have to code in like languages like C++ that are a lot faster. And they're a lot more difficult to write in. You can't do it in Python. We're making very simple games here, but like the video game writing industry has a lot of really advanced stuff going on, and they make use of like graphical processing units, and you're coding multi-processing, all that stuff. So it's really hard to write a video game that looks smooth and like all that stuff. So simulations are in some ways easier to write than video games, but they're harder to understand. That's the way I envision it. So yeah, and I just wanted to like show some pretty quick like videos and pictures and stuff from cool simulations. So these are like, this is like cutting edge, like this is the premier standard for like astrophysical simulation. So like on the bottom left, that's like a simulation tracing like light rays moving around a black hole. It's pretty cool. Like up there on the top left is like I think it's a neutron star, and it's like gas flowing around the neutron star. Maybe it might even be a black hole, I don't really know, but it looked cool. On the right is like galaxies forming, I think, or like supernova explosions and stuff up there, I don't know. But like a whole bunch of these things are like simulating tons of laws of physics all at the same time, like 35 equations, like 100 equations all simultaneously, partial differential equations, big brain stuff. But like you kind of understand what they're doing. Like after everything I just said, it's the same thing. The only difference is the equations are harder. and they have to be more accurate. So they have to like be really careful with the way they update every time step, but like you're still doing the same thing. And so in a lot of ways, these are like the same thing as video games, just really complicated physics. And interpreting them is difficult sometimes, but it's really cool. And you can like analyze them and compare them to reality. And it's really cool when like that simulation of a black hole happened to line up perfectly with the simulation, or not the simulation, with the actual picture we took of the black hole. When you blur it out due to like some like, you know, seeing and stuff, when you take that simulation, you blur it, and then you kind of like take a snapshot of it, it actually lined up perfectly with the image of the black hole we took. And wow, that's like, Einstein was right. Holy shit. Like, whoa, that's cool, right? So like simulations are really cool, and they make pretty plots. Hopefully everybody knows that you can make really pretty plots. That's the I Am Show up there on the top left with lots of subplots. Yeah, with color bars and stuff. Well, that one's a color bar somewhere in there, but you get the point. You can make all those plots. If you have the data, you can make them. It's pretty cool. I think that's everything I have. So yeah, let's see. 45. So we have a little bit of time left over. So get in your groups and just kind of talk about your projects. So all we have. The lectures are going to be shorter from now on, in case you haven't noticed. So you have a little bit of time to talk with your group mates. But yeah, that's all we'll be doing for the rest of the lecture, is just talking. Hope you enjoyed the cool lecture. Where's my Zoom? Where is the Zoom? Oh, right. Escape. Haha. All right, let's stop.